Differentiation.
Mr. DiGiovanni?
Yes.
What's the deal with the squares?
Oh, that's so I can focus my camera. I need something that's like high contrast. So, because if I do a manual focus and I set it, because if not, when I'm walking, it'll focus on me and then the board and then me and the board, and it's annoying. And nobody really needs to see me, right? So. Yeah, I've used that when when I'm not using the projector. I have like a little checker thing I'll use instead.
A question about like the notation. So like when you're finding local maximums and minimums, you like find the x value and then plug it in.
And get the y.
But is will you have to do that on the test, or like, because I mean, some of these like trying to think.
If I ask you for the local max and min values, all I want is the values. So you can just give me the y coordinates.
Okay.
But it doesn't hurt to put the x there also.
Okay.
Is that answering your question?
Yes.
Okay. Uh-huh. No. We're going to do that today, but that's not on the test. All right. Well, I'm cold, so I'm going to keep my jacket on, I think. So we are trying to wrap up this chapter, well, this section at least. Sorry, we already did this section. We're trying to wrap up the chapter. We've got this section, curve sketching. And this is where we kind of bring everything together. All right? We bring everything we've learned in college algebra, pre-cal, stuff we know about limits, all the stuff we've learned about how the first and second derivatives tell us about the shape of a graph, to basically take an arbitrary function and try and graph it by hand. Now, you could argue that this is somewhat of an obsolete sort of idea, especially since you can just walk to the computer and get the graph, right? So I think the way I like to look at this is just, I don't know. You have to kind of look at sometimes math classes for what they truly are at this level, and that is kind of like a history course. You know, we're trying to talk about math that was developed many, 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 many years ago. Oh, you know, and it's been basically humans thinking about math for thousands of years. And we're just kind of looking at some of the major accomplishments. And one of the major accomplishments that we had because of calculus was the ability to draw a curve, sketch a graph without a computer, right? So nowadays it's not as practical, but it does bring everything together, which is worth us looking at, all right? So there's kind of a set of steps, kind of a procedure we're going to use for sketching graphs. We are going to first look at our function, make sure we understand what the domain of the function is. We're going to see if it's possible to find any x and y intercepts for our function. That would be something you would have done in college algebra. We're going to check for symmetry. So we're going to be looking like a parabola, right? Is symmetric. It looks like a reflection of itself. So we'll be looking at them and say, hey, you know, can we tell by just looking at the function whether or not this is symmetric or not? The sine function is symmetric. We're going to be finding asymptotes. So back in college algebra, you study vertical asymptotes and horizontal asymptotes. And in this class, we studied them. We studied vertical and horizontal asymptotes when we were talking about limits. So we'll get back to this. Then we start to pick up the rest of this section, which is steps 5 and 6 and 7. And that is figuring out where our function is going up, where it's going down. We're going to find any local max min values. We're going to determine where it's concave up and concave down. We're going to identify any inflection points. Then we're going to do this step 8, which is we're going to make a table, and then we're going to sketch the curve. So these problems are going to take us a while. All right? Got it? So here we go.
So is the test just going to be like, what are these problems? Pass or fail?
Yeah, so this is not going to be on the test on Thursday, okay? It's not. This is not on the test on Thursday. The test on Thursday stopped at the end of the last section. So this will be on the final exam, all right? Okay? So yeah, and I mean, I'll give you one problem, but on the final we have what, like close to 3.5 hours to take the test. So we'll have more time for a question like this. All right, so here we go. Let's start with something that we could probably sketch without calculus. But now we're going to see we're going to have a little more detail with this function. So I'm just going to pick one out of here. How about f of x equals x over x squared minus 9. Okay, that would have been something that we did in college algebra. That's a rational function. If you, in college algebra, went through this, you'd figure out what the x-intercepts are, you'd figure out where the vertical asymptotes are, you would figure out your horizontal asymptotes, you draw it, right? If you had slant asymptotes, you might have talked about that in college algebra. We are going to add to that by using the calculus we learned, right? So let's start with domain, all right? So what about the domain of this function? What can you tell me about it? Can't equal, x can't be 3 or negative 3, right? Because we have division by 0. So I'm just going to say x cannot be equal to plus or minus 3. So when we draw a graph at an x value of 3 and negative 3, we have no graph, right? No graph. All right, what was the next thing on our list? So we have x and y intercepts, right? So we're going to look for x and y intercepts now. So how do we find the x-intercepts for any function? Set the function equal to 0, right? Set the function equal to 0. So we're going to set x over x squared minus 9 equal to 0. And that is a fraction, right? A fraction equals 0, and a fraction can only be 0 if the top is 0, right? So we just have one solution here. X is 0. All right, and what about y-intercepts? How do we find our y-intercepts? We plug 0 into the function, right? So we actually plug 0 in for x, and that output is where we hit the y-axis, and that's going to be at 0, right? So you don't need to draw this right now, but this is what we know so far, all right? Don't draw this. At 3 and at negative 3, we don't have graph. And at 0, we have an x-intercept, right? But that's also where we have a y-intercept. So we know our graph passes through that point, right? That's what we know. My mic fell. Oh, yeah. It was attached to my graph. Thank you. I was at HEB the other day after class, and I had my mic on still. And I was wondering if the person thought I was recording them or something, Hello. Checking your customer service here.
Secret shopper.
Secret shopper, yeah. Okay, so x and y intercepts, good? All right, now in terms of symmetry, for symmetry, I would say on this step, this is kind of like if it's obvious to you that it's symmetric, then let's state it. If it's not obvious, let's just move on. All right, so this right here, you might look at this and just not be sure. Like if this were just like x squared, like parabola, I think you would say, okay, yeah, we've got symmetry. But I don't want you to have to go very far in your mind for this. If it's not obvious, just move on. We'll have more than enough information to graph it, even without that aspect of it. Okay, so, we've got the symmetry. We're just not even caring. What was next? I don't have these steps memorized. Asymptotes. Okay, so for asymptotes, we have two types of asymptotes to look for, vertical and horizontal. So let's look at vertical asymptotes first. So where would you ever have a vertical asymptote on a function? They would occur whenever the denominator is 0 and the numerator is not 0. So we already know what makes the denominator 0. 3 and negative 3, right? And not only do we know that, but at 3 and negative 3, we get 0 on the bottom, but we get something non-zero on the top. What I'm getting at is What if we plugged in 3 and we got 0 on the top and the bottom at the same time? That would be a hole in the graph. That would not be an asymptote. So we have to be looking for places where we have something non-zero on top and something 0 on the bottom, which in this case is at 3 and -3. So we have vertical asymptotes. They happen at x equals 3 and -3 because we're getting division by 0 and the numerator not 0, right? So we know right here, again, you don't need this graph. I'm just kind of helping us construct it mentally here. We know this much now, right? We knew at 3 and -3 we didn't have graph, but now we know these are vertical asymptotes. So our function, when we get close to these dotted lines, are going to take off and do something like that, right? Okay. What else? How about horizontal asymptotes? Well, that's going to tell us what's happening at the ends of the function, right? To the right forever and to the left forever. So to do that, we're going to just take some limits. We're just going to say, all right, what's the limit? Let's go out to the right first, as x goes to infinity of this function. Make sense? We want to know what's happening as we go that way and draw the function. Does it flatten out to something? So we take this limit. We say what happens as x goes to positive infinity. We get infinity over infinity, right? L'Hopital's rule, right? We can use it here. So L'Hopital provides us with the derivative of top, which is 1, derivative of bottom, which is 2x. And what is that limit as x goes to infinity? 1 over infinity, which goes to 0, right? So that goes to 0, which means that as I draw out this way, right, I should flatten out to 0. So over here on the side, I'm just going to put a dotted line. And I'm not going to draw it all the way through. I'm just going to, just to the right side, I'm going to draw a little dotted line. This is not my final picture. Again, this is me kind of just showing you what we know so far. We still need to go out to the left side, though. Okay? We still need to go the left way. So how am I going to do that? Let x go to negative infinity instead, right? And does that change our answer? No. It doesn't, because we still get infinity over infinity. Doesn't matter if it's plus or minus. Just top's getting big, bottom's getting big. We do L'Hopital again, and when we do L'Hopital, we should get 0. All right? So that means out the left side, our function's going to flatten out to y equals 0. So out this side flattens out. Okay? Any questions? All right, now step 5 is where we start bringing in the calculus stuff. Well, the limit was calculus, so I guess we've already started that, but now we're going to start taking derivatives, right? So we want to know for step 5 where this function is increasing and decreasing. So for step 5, I take a look at my function. I need to take its derivative. So the derivative of that, we're going to need chain rule. We're going to need quotient rule, right? So the derivative of this will be, let's see here, derivative of the top is 1 times the bottom minus the derivative of the bottom times the top all over the bottom squared. And I'm going to have to take that and I'm going to have to look at two things. Where's this 0 and where's this undefined, right? Those will be the critical numbers. So let's clean it up first. I think we get negative x squared minus 9 on top. And on the bottom we get x squared minus 9, that quantity squared. Right? Nothing cancels here, right? These are not like factors. So that's our first derivative, right? So let's figure out where this thing is 0. Where's the derivative 0? Okay, so if I set this to 0, I only have to set the top to 0. Am I moving too fast, or is this a good speed? We okay? All right. So we got that. I'm going to move the x squared to the other side. So it says, so it becomes this. And what can we say about that? Can x squared ever be negative 9? Not unless you're using imaginary numbers, which we're not. So this has no solution, right? So we have no critical numbers for this yet, right? So this is never true. What is the other thing we have to look at? Where it doesn't exist. Okay, where would that derivative not exist? So here's our derivative. Where would that be bad? 3 and negative 3, right? But those points were not in our domain, right? So are they still critical numbers? I told you kind of, sort of, no. I mean, technically, to be a critical number, you have to be a number in the domain. But we're still going to put them on a number line, okay? We're still going to put them there. All right, so now we go to a number line, yes? So this we don't have, kind of, sort of. It's a little tricky. So I'm going to put on my number line what? Just negative 3 and 3, right? That'll break up my number line into 3 regions, and now I need test points in each region, don't I? So I need a test point here, test point here, test point here. So how about negative 4? How about 0? And how about 4? And where do those get plugged in? First derivative, okay? First derivative. So I'm going to plug into my first derivative, negative 4, plug into my first derivative, 0, plug into my first derivative, 4. And I'm just looking for positive or negative, right? This is actually going to be really easy to do, because you actually don't even need to look at any of the numbers. Just look at this quantity for a second. Would you agree that x squared is positive, right? No matter what? I mean, it could be 0, but positive, and then I'm going to make it negative, and then I'm going to subtract 9. So the top is negative no matter what. No matter what. And the denominator is positive, right? So long as I don't plug in 3 and negative 3, but I'm not. So do you all agree we're going to have a negative over a positive no matter what I do? If I have negative over a positive, then all of these are negative, right? No matter what. Which means our function is always decreasing. Our function here is decreasing. Function here is decreasing. Function here is decreasing. Right? No local max, no local min. Now just as a check, what if this one went up? Would we have a local max and min? We would not have local max or min, because we're going down then up, right? Where? Here, but that's not in your domain. So you don't have a local min. And you wouldn't have a local max either, because you go up then down, but it's not defined there. And we'll see this when we look at the graph. So just be careful with that. All right, so no local max, no local min, right? No local max, no local min. So I'm just going to put over here no locals, no loco, no locos, no locos. Let's just put no locos. That just seems fun. All right, now what? Second derivative, right? We're going to be working with the concavity and inflection. So this is step 6. So I need to take the derivative of the derivative. So I need to take derivative of this, right? So I'm going to have to use the quotient rule again. Derivative of the top is negative 2x, right? Times the bottom. Minus, okay, now be real careful on the bottom here. The derivative of the bottom is going to require what? Chain rule, right? So derivative of this is 2x squared minus 9 to the first power, right? Times 2x times that whole ugly thing, right? That whole ugly thing, which is negative x squared minus 9. Okay, all of this over the bottom squared. So it's going to be to the 4th power, isn't it? Because we're squaring something that was already squared. Any questions on that quotient rule? We got to set that to 0. Okay. So I hope that some of the algebra like this has appeared in the homework. I know it has, because I've talked to some students about this, right? This sort of algebra. We're going to look at this. This is going to be like its own little monster here and this own little monster here. And we're going to try and pull out a GCF from here and here. So in terms of numbers, what number can I pull out of both of these? I can pull a 2 out, right? And I could pull the negative if I want, or leave it. It's up to you. I'm gonna pull the negative also. So I'm gonna pull a negative 2 out. Okay, in terms of factors, there's an x factor in this one, right? And there's an x factor in this one. So I can pull that x out of both. What other factors can I pull out? There's an x squared minus 9. There's 2 factors here, and there's 1 factor there. So I can pull out 1 factor of x squared minus 9. And is there anything else I can pull out of all these? I think that's it. That's it. Nothing else. Is that all right? There's, okay, so we're looking at these as like separate things. I'm trying to find something common in both of these. So since they both have a negative 2, I pulled negative 2. They both have an x, pull the x. They both have x squared minus 9, pull that out, right? But that's all they have in common. So now you can use parentheses here. I'm going to use a bracket because, I don't know, why not? Brackets and parentheses have the same weight, okay? I mean, I know when you're learning arithmetic early age, you're almost taught like brackets are somehow different than parentheses. They're the same, all right, in terms of order of operations. All right, so this has to distribute through and get back this. So really, what did we leave here? Like what was left when we pulled everything out? Just one of these factors. So I have an x squared minus 9. I don't need it in parentheses, but I'm going to leave it in parentheses. And then we pulled the negative out. We pulled a 2 out. We pulled this out, right? And the x. So all that's left is a plus 2, right? There's still a 2 there. And then that negative x squared minus 9 factor is still there. So that's our numerator. All over that big ugly denominator. That's actually not that big and ugly. If we expanded it, it would be, right? Okay, so a couple of things are going to happen here. I have this factor right here, cancels with one of these. So this 4 becomes a 3. And then this can be cleaned up, right? I can get rid of parentheses and stuff there. Let me do that. To save myself some room, I got x squared minus 9 minus 2x squared minus 18. Do you all agree? Yeah? Okay? And then combine those things in blue together, and we'll have our, I think, our final result here. Negative 2x, and then everything in the brackets becomes what? Negative x squared minus 27, right? All of that over x squared minus 9, that quantity cubed. So that is our cleaned up version of the second derivative. Yes?
Oh, so we're eventually going to set this to does not exist, right?
0 and does not exist, yes.
So then when we, so would it be all right then to like simplify it like that? Because then, like, would it interfere with the, like when we set it to does not exist, so it would have to be like a number over 0.
Mm-hmm.
So like, would x squared minus 9 raised to a power of 4 be significant as compared to like x squared minus 9 to the third?
No, because whatever makes x squared minus 9 0 is going to make it to the third or fourth power 0. So it doesn't matter if you raise it to the third or the fourth, you're still, if this is 0, you're in trouble, right? Am I addressing your question?
Yeah.
Okay.
And real quick, canceling out the one on top, would that affect 0?
Would that affect 0?
When you set it equal to 0?
Nope.
Okay.
Mm-mm. I understand your question. I understand your question. What's being suggested here is that when we cancel this factor, right, there's kind of a subtle little rule here. When you cancel this factor, you have to kind of make a promise that you're not ever going to let that thing be 0. Let me give you an example. Way back in the beginning of class, we were talking about limits. We said that if you look at that expression and do a difference of squares, right, like that, then these factors cancel, right? And you just get x plus 3. Right? So if I ask you over here, what would make this numerator 0? You would say 3 and negative 3, right? But if you come over here and look at this expression and say, what would make this 0, you're only going to say negative 3, right? You've actually lost one of your answers. And I think that's what you're concerned about, is if I cancel this, am I going to lose one of my answers? Well, here's the thing. When we cancel these, we're actually kind of making a promise, and I told you all about this way in the beginning. When you cancel two factors, you're kind of making me a promise that they're never 0. And so whatever you cancel here, right, you're kind of telling me x cannot be 3. Like I can't cancel this. Because you get 0 over 0 here if I let x be 3, right? So the problem that we eliminated by taking this out, it still appears here. Like that problem still exists, doesn't it? 3 and negative 3 still exist as an issue for us. And we're going to pick it up when we do the does not exist part of the second derivative. Good question. Really good question. All right, let's set this thing equal to 0. So when we set that to 0, right, we have negative 2x times negative x squared minus 27 equals 0. We're just setting the top to 0. And that breaks down to be two things. Negative 2x is 0. That's one equation. And then the other one is negative x squared minus 27 equals 0. This one here just has one answer, 0. And this one over here? Two answers? No solution. We run into that same problem we had earlier. If I move the x squared to the other side, I get something squared is negative 27, not going to happen. Okay? So we only have one answer for setting the second derivative equal to 0. Now we need to ask ourselves, where is it undefined? Where does the second derivative not exist? And we would say x is 3 and negative 3, but they're not in the domain. But we're going to put them on our number line, right? So we don't really have this, but we kind of do. But we don't. But we do. We don't. Technically, we don't, okay? It can't be both. There's actually a very fundamental principle in logic. Where's my logic? Logic, right? Have you all talked about the law of the excluded middle? The law of the excluded middle says that pretty much given any situation, any statement, it is either true or false, and there is no third option. So the law of the excluded middle, there is no middle option. So 3 and negative 3 either are critical points or they are not. Technically, they are not, but they're still going on a number line. All right, so isn't this pretty much, does that look exactly the same as the other one? Didn't we have those same numbers? Oh, no, we didn't have 0 on the last one, did we? We didn't have 0. Test points, right? Now we need test points. Negative 4. Negative 1. 1. 4. Where are those going? Second derivative, which I erased. Okay, it's all right. So those are going into our second derivative. This time it's going to matter, all right? So we need f double prime of negative 4. We need f double prime of negative 1. We need f double prime of 1. We need f double prime of 4. And our second derivative was negative 2x times negative x squared minus 27 over, I think that's what it was, x squared minus 9, that to the third. Wasn't that our second derivative? Okay, so we need to plug in some, let's take care of a couple of things first. What can you tell me about the denominator? Always what? Is it? Hold on, this isn't always positive. Sorry, I forgot. It was fourth earlier, so yeah, we actually have to think about that, don't we? But what can you tell me about this? Always negative. That's always negative. Right? So this right here, though, could be either negative or positive, depending. So what I'm getting at is I'm only going to look at these two pieces. That's all I'm going to look at. And then I'm going to remember I have a negative here. Okay, so when I plug in negative 4, What do I get in this top left corner if I plug -4 in right here? I get -2 times -4. That's going to be +8, right? So I get a positive number. But then I'm going to be multiplying that times that negative quantity right here. And then dividing it by, let's see, -4. What happens if you plug -4 in here and then subtract 9? So -4 squared is 16. Take away 9, right? So that's a positive number. Cube it, still positive, right? So the ratio of a negative on top and a positive on bottom means we have a negative here, right? And we just need to do that for the remaining test points. So how about at -1? Plug -1 here. Positive there, negative here. So positive and then negative over, let's see, we're plugging in -1. So -1 squared, +1 minus 9. So -8 cubed is still negative. So now we have a negative over negative, which is going to be positive. And will it always just switch? No, it doesn't always switch, all right? So you have to check these. How about at 1? Plug 1 in. You get negative here. So you have negative and negative, which will become positive. And then the bottom, you have 1 goes in there, you should stick with negative there, right? Sorry, negative. And all of that together will be negative. And then the last one's going to be positive, okay? I'm not going to check it, but it's positive. All right, so it does switch in this one. It does. Right? Okay, so let's go back to our little chart here thingy. We have at -4, we have a negative second derivative, which means our function is doing what? Concave down. And then we're going to be concave up. Then we're going to be concave down. And then we're going to be concave up. Inflection points? At 0. That's the only one, though. Not at 3 and -3. Because, again, these points are not in our domain, right? But at 0, 0 is in our domain. And we have a switch from a positive, right, concave up to concave down. So that's an inflection point. So we have an inflection point at x equals 0. If you wanted to say that a different way, you could say at f of 0 equals 0. Now, that's me telling you both the x-coordinate and the y-coordinate of the point on the graph, on the original graph, right? You plug in 0 to the original function, which is where we have the inflection point, and it's spitting out 0, isn't it? Okay. Like 30 minutes in. What's next? We've determined the local max and mins, where they occur. We determined the intervals. Oh, I forgot to switch to 7, didn't I? And inflection points. Okay, make a table. Step 8. All right, so let me tell you a quick little story. Do you remember, I told you a story, I think, earlier in the semester about a student I had when I was a teaching assistant that had come into the tutoring lab, like kicked the door down and was like, you need to tell the class that you messed up. Do you remember that story? Okay, so when we got to the point in the class where we were about to do what I'm about to do, I showed the class how to do it, and the way that I show them is not a way that you're going to see in a book. Like, I've never seen it in a book. I've never seen anyone do it this way. It's just the way that I have done it. It's the way that made sense to me. So this student that didn't like me, he called it the Bobby method. And so my name is Robert, and I used to tell my classes, I go by Robert, but don't call me Bob or Bobby because I don't like Bob or Bobby. That's just not me, right? So he called this the Bobby method. Right, just to kind of me, So we're gonna. I like it. It's stuck. So this is the Bobby method. All right. So what we need to do is try and put the information we just gathered into a format that will help us graph. So the idea here, and don't write this yet, is I'm going to have a graph right here. Okay, I'm going to draw a graph here. But directly above it, I'm going to make a table that's going to help me with this graph. All right, so just on your page, make sure you have enough room, okay, vertically for a table and a graph below it. All right, so here's what I'm doing. I'm going to start my table first up here. What I'm going to do is I'm going to draw a number line. And on this number line, that's a number line, I'm going to put any critical points that I found from setting the first derivative to 0, any critical points I got from setting second derivative to 0, any points that were not in my domain, like -3 and 3, right? All those important points I'm going to put on my number line. Okay, so I'm going to put what 0 was a critical point we got from the second derivative, right? And then we had 3 and -3. Those were critical points that we had. They weren't critical points, were they? Sorry, no dots. Those weren't critical points, but they were important points, right? Okay, that was it though. There wasn't anything else, right? So then from this, I'm going to draw some lines straight up, not dotted lines. Make sure that you leave yourself a little bit of room here on the side, okay? And then what I'm going to do is I'm going to put some rows in here. And I only want enough room for 3 rows. 1. So I'm going to draw 2 more lines like that. And now I'm going to have a total of 3 rows, right? 3 rows. And then I have these columns that were created from our important numbers, right? So here's how we're going to fill out this table. The first row is going to tell us about what the first derivative told us. The second row is going to tell us what the second derivative told us. And the top row is actually going to be our overall, like what it all tells us about the function. And let me just follow me through with this one time, all right? So go back and look at the thing you drew earlier for the first derivative. We had down, 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 didn't we? Yeah. Isn't that what we had? So if I come to this table and I ask you, look, to the left of -3, if I'm talking about first derivative, I'm going down here, right? So our function is supposed to go down here. How about between -3 and 0? Down. It's also down because that. And then here between 0 and 3, down. And then between 3 and on, down. That one's easy. They're all down. You can't mess that up, right? Okay, what about the second derivative? So go look at that. To the left of -3, what were we? Concave down, so I'm going to draw a little frown, okay? Between -3 and 0, what were we? Concave up. And then between 0 and 3? Down. And then here to here, or here on? Up, right? Okay. Now we're going to put these things together. So to the left of -3, I need our graph, right? Our graph of f has to be both decreasing and concave down simultaneously, right? So when you look at, if I tell you concave down, imagine splitting this down the middle. On the left side of this, you would be increasing, wouldn't you? And on the right side, you'd be decreasing. There's only one way to be on a frown and be decreasing, right? And that's to look like the right side. Yes? So what I know about this function f is that it has to look like the right side of a frown. So to the left of -3, I must look like the right side of a frown. Understand? How about between -3 and 0? You have to be decreasing but smiling. Which half of it? Left half, right? So you have to look like the left half of a smile on that interval. And then how about between 0 and 3? The right side of a frown, right? And then how about from 3 on? Left side of a smile, right? So if you open up a textbook on this, like I said, they're not going to do this at all. They use these things called sign charts, and that's the way I learned it, and it just confused the hell out of me. I'm just like, what? You know, they're like, it would tell you like, if your first derivative is negative and your second derivative is negative, then a negative times a negative is positive, and when you have positive, then the function does this, and it just got too much. For me, it didn't make sense. This to me makes sense. Hopefully it makes sense to you. All right? So if you go to a tutor and they start using sign charts, Just be prepared to be confused. All right, so now I'm going to draw my graph. Here's my y-axis. Here's my x-axis. And notice I lined it up perfectly. Here's 0, right? 0. I'm going to bring everything down. Here's 3. Here's -3. And now I start to put all this information together. So from the top, the domain we had checked, right? X-intercepts and y-intercepts we had checked. We got this point right here, right? We had symmetry we skipped. We had asymptotes, didn't we? We had an asymptote here. We had an asymptote here. And we had out the edges, right? I hope that when you were in college algebra, you were told that when you draw horizontal asymptotes that you never draw them through the whole thing. You always draw them at the ends. No? You drew them all the way across?
Yeah.
Danger zone. Why is that dangerous?
So it can cross the whole.
Yeah, because if you have a dotted line across here, you might think that you can't cross it, but you can. The horizontal asymptote only tells you about end behavior. It tells you nothing about this. Now, vertical asymptotes you can't cross, so it's okay to draw them up and down, but horizontals, never draw them all the way across, right? I mean, you can, but just...
Even when it's like at 1?
Even if it's at 1.
You're just gonna...
Even if the horizontal asymptote was at 1, you'd only draw dotted lines out here. Look, this is going to be a perfect example. When we're done, you'll see what I mean. So, okay. What else do we have? Horizontal, vertical, increase, decrease, concave up, concave down. That's all, right? So, if I had to draw this right now, here's the best I could do. I know this point exists, right? That point exists on my graph. And I know between -3 and 3, sorry, -3 and 3, -3 and 0, I must look like that, right? So from that point, I know that I must draw this. And the vertical asymptote forces me up, right? And it looks like the left side of a smile. Now, when I get between 0 and 3, what does it have to look like? This, right? So it's going to go like that, okay? Inflection point. Smile becoming frown. Now, over here, I know what it needs to look like, and I know I have this, but I don't have any reference point, do I? I don't have a point to work with, right? If I had a point, then I could start drawing that. But I don't know if my point is above or below. And it can only be above or below. It can't be both, right? Why can't it be above? Yeah, if I'm going to draw that, and let's say I had a point up here, right? And I were to draw that, then I would have to go I'd have to cross through the x-axis, wouldn't I? Which I can't do. I can only cross here. Which means the point has to be down here. And now it has to look like this, so I'm going to just kind of draw it like that, right? That's the right side of a frown. Asymptotically approaching 0 this way, and vertical asymptote, so it's headed to -infinity there. With that same logic over there on that side, the point would have to be where? Up on top, right? Now you could check. You could just pick a number 5, plug it into the original function, it would spit out a number, all right? But we don't really need that much if we understand how the picture is going to dictate what this looks like. There we go. That was a lot of work. That's 45 minutes of work. I mean, it's a lot, right? I said I wanted to start with a function that we were familiar with, right? So if I go to our graphing utility and I do x over x squared minus 9, I would say that my picture's better. No, I'm just kidding. Right? You got it though, right? You get the idea? So if this worked for, the big difference between this and college algebra is that this doesn't work just for rational functions. This works for any function, right? So now you can get something very abstract using the same method and get a really good picture of it without needing a computer. All right? Okay, so let me go back to this thing that I was talking about, drawing the horizontal asymptotes all the way across. If you were to have drawn this horizontal asymptote all the way across, I'd be a little bit concerned about how you feel about drawing this through that horizontal. Students are tempted, at least in college algebra, to just always avoid dotted lines. But you're actually going right through it here, right? So that's why I say don't draw them all the way across. Just do them at the end. Yeah, like you might want it to do this instead, but that's not what happens. So, okay. You ready for a more interesting function? Yeah?
Can we do one?
We can do one, yes.
I have,
You have one?
I do have one.
Now, are you making this one up or are you getting it out of the book? Which one?
Question number 35.
35. 1 over 1 plus e to the negative x. Wait, what are we? $35? What section are you in? Oh, that's 43. I mean, sorry, 4.3?
Yeah.
Well, that one's on a closed interval. Yeah, maybe if I have some time. Let me do something else first, because that is just a trig type function. I want to do something that pretty much everyone in here would probably look at and just not know what it looks like, you know? I'll let you choose. So you get to choose between these two. Y equals the square root of x squared plus x minus x. And the other option I'll give you right now is y equals x e to the negative x. A or B? A, B. So how many of you want A? B? Okay, we'll do B first. If we have time, we'll do A later. Okay, so let's do this one. I'll call it f of x instead of that. All right, first step, domain. And this might help with the domain. This is the same function, isn't it? E to the negative x, you really just drop that down as e to the positive x. So do we have any domain issues here? No, there's no way you can make e to the x 0, right? So domain is all real numbers. Everything. Okay, second step, x-intercepts. How do we find the x-intercept? Set it equal to 0. But if we look at it that way, it's a fraction, right? So just set the top to 0. So x is 0. Okay, how about y-intercept? Plug 0 into the function. And you get 0 over e to the 0. E to the 0 is 1, so you just get 0. So isn't that the origin again? Isn't that point right in the middle? Okay. How about symmetry? E to the x by itself is not symmetric, right? If you just look at e to the x, that's e to the x. That's not symmetric. It's not a reflection of itself. So I doubt we're going to have symmetry in this problem. So I'm just going to skip it. Like I said, don't get bogged down on symmetry, all right? What's after symmetry? Asymptotes. Okay, so let's start with vertical. Vertical asymptotes. Where do we have vertical asymptotes? Anywhere where the denominator is 0 and the numerator is not. We don't have any. Okay, how about horizontal asymptotes? All right, there we have to take some limits. We have to take the limit as x goes to infinity, and we have to take the limit as x goes to negative infinity. Is it possible, just a quick question, is it possible to have a horizontal asymptote that goes out the right side that is different than the horizontal asymptote that goes out the left side? Can these be different? In college algebra, no, because you're studying rational functions. But in calculus, you can. Something going the way it behaves out the left can be different than the way it behaves out the right because the functions are different. With rational functions, it's the same on both ends, whatever's happening. So, well, I should say it this way. If there is a horizontal asymptote with a rational function, it has to be the same out the left and right. Okay, so let's do this. Limit. Let's go to infinity first. So you get infinity over infinity. L'Hopital. So one time with L'Hopital here. Derivative top, derivative bottom. And we get 1 over infinity again, which goes to 0. So the x-axis. Okay. So out the right side, we're going to have a dotted line just out there off the x-axis, right? Okay, what about going the other way? Limit x goes to negative infinity of x over e to the negative x. This one's a little tricky. I don't know why I put negative x there, sorry. So where's the top headed? Negative infinity. So this is headed to negative infinity over, yeah, this one's a little weird because you're saying what happens is as x goes to negative infinity of e to the x. So you're really looking at the e to the x function and you're trying to go this way, right? And that goes to 0. So the bottom goes to 0. And have we ever had that? I don't think we've ever had negative infinity over 0, have we? So maybe we just give up. No, here's what we do. We look at it a different way. Let's go back to the original problem before we wrote it as a fraction. Now if I let x go to negative infinity, what does this look like? That's headed where? Negative infinity times. Now where is that heading? So if you plug negative infinity up in here, you're going to get negative infinity, which is positive infinity. So that's saying e to the positive infinity, which is infinite, right? Infinitely large. And so this is going to positive infinity. And so what do you get when you do negative infinity times positive infinity? Big negative infinity, right? Another way you could have looked at it is back here, the numerator is like, hey, I want to get big, right? And the denominator is like, well, I want to get small. And normally when denominators get small, fractions get big, right? So it's like this guy wants to be big, and this guy, because it's getting smaller, wants to help that guy get bigger, if that makes any sense. But if we just revamp it, it's just this. So it becomes negative infinity, or goes to negative infinity. Which means out the left side, what's happening? It's dropping down, right? It's going to drop down forever. Out the right side, it's going to flatten out. So this is an example where we have different things happening out both sides. All right. Verticals, horizontals, derivative time, right? Okay, let's do our derivative. The first derivative of this function, we're on step 5. First derivative of this function, you have options. Product rule or quotient rule? Your choice. I don't care. What do y'all want? Product or quotient? Product? Any quotients? I don't care. Product? Yes? Okay. Product rule it is. So if we do product rule here, derivative of the first one, which is 1, right, times the second one, plus the derivative of e to the negative x. Be careful. The derivative of e to the negative x. It's itself e to the negative x times negative 1, right? Because you have to do chain rule, you have to do derivative of what's up here. And then you can move on to finishing the product rule and hitting that with an x. What happens if you miss that negative 1? It's over. It's pretty much over at that point, okay? That's how critical that negative is, because everything's going to be off after that, right? Not only will your number line with your critical numbers, that'll be off, but then your second derivative is going to be off. Yeah, that would suck. Okay, so e to the negative x minus x e to the negative x. I'm just cleaning it up. made this negative come out here to make that minus, and then brought the x out in front. And that's my first derivative. I need to figure out where it's 0. I don't have a fraction. Well, I could write that as a fraction, but yeah, I can just factor an e to the negative x out. Right? They both have it. They both have an e to the negative x, so let's just pull that thing out. So now we set both of these factors to 0. This can never be 0. E raised to anything can never be 0. And so I don't have to consider that, set that to 0, I just get x is 1. So I only have one critical number here so far. 1 is in our domain, because our domain was all real numbers, so we're good with that. How about where this thing is undefined? Does this derivative ever not exist? It's a well-defined function. Look at this thing. Look at this, right? I can plug any number I want in here. Never going to have any division by 0 or problem. Any number here, we're good. So this is never an issue. So my number line will have only one number on it. It'll be the number 1. And now I pick some test points. One to the left, one to the right. I'm going to go with 5. Anybody watch that game last night, that San Francisco-Seattle game? That was a heck of a game. It's a good thing I'm not like a big San Francisco fan or a big Seattle fan, because I think I would have had a heart attack a few times. It was a great game. All right, so plugging 0 and 5 into the derivative, right? Okay, let's do that. What's the derivative at 0? What's the derivative at 5? So we're supposed to go into this, right? So I'll write it down. E to the negative 0 minus 0 times e to the negative 0. What's e to the negative 0? What's e to the 0? 1. And then 0 times anything is 0, so this is just going to be 1. So that's it. We just get 1 out. Positive number. So that means our function is increasing here. Then we plug in 5. E to the negative 5 minus 5 times e to the negative 5. You could use a calculator here, but you could also do this. Just factor out the e to the negative 5, right? That's kind of dumb, but yeah, I guess you could. I could have. That's so stupid. I don't like that. This is just negative 4e to the negative 5. I guess you could look at it that way. This is e to the negative 5, one of them, right? And you're taking away 5 of them. So now you have negative 4 of them. We know e to the negative 5 is always going to be e to any power is going to be positive. So that's a positive number. And then times a negative number. So you get negative. So we got decreasing here, don't we? Or use your calculator, right? So our function is decreasing here. Do we have a local max, local min? Local max. We have a local max because 1 is in the domain. So we have a local max at f of 1, don't we? When we plug 1 into the function. And what do we get when we plug 1 into the function? Yeah, you just get 1 times e to the negative 1. That's just e to the negative 1. Which is the same as 1 over e, right? If I plug 1 in here and 1 in there, I get e to the negative 1. Which is a number, right? Whatever it is, it's a number. Okay. What's next? Oh, no local mins, right? No local mins? We never went down then back up. All right, so next step, step 6, second derivative. Second derivative of this function. You know what I'm going to do? I'm going to go back to this right here, and I'm going to factor that e to the negative x out and do 1 minus x. I like this because if I do this, I can just do a product rule right there, couldn't I? I can do derivative of this times this plus a derivative of this times this. I kind of like the idea of doing that as opposed to doing this separate from this.